Welcome back to Unit 6, Day 5. And today, I know it's going to be your favorite because we're going to really get into some conceptual things and understand how this is all applicable in the real world. And you're always like, when am I going to use this? Okay, so we're going to be talking about the fundamental theorem of calculus, finally, like in its wholeheartedness. Okay. And then we're going to have some other things with positions and velocities and distance and displacement. And we love that. Okay, so first thing we're going to do is the fundamental theorem of calculus. You're like, what? I've been in calculus for over a semester and I still don't know the fundamental theorem? Well, now you will. So the fundamental theorem of calculus says, if I have this function and I am integrating on a continuous function from a to b, then I take the antiderivative of the function and plug in the value of b to that and subtract the antiderivative of this function and plug in the value of a to that, and I have an answer. Now, I won't have a plus c because this c and this c would just cancel for both of those functions. So when I have these bounds on the integral, we do not need a plus c. When we have bounds, then this whole integral is called a definite integral. When I don't have bounds, it's called indefinite. Okay, so we're going to take the antiderivative of x, and then we're going to take and evaluate it. This is kind of how I show it, from a to b. So I plug in my b, and then I plug in my a. And I do the subtraction, and I get some numerical answer. So my answer is always a number when I have a definite integral. Back before, when we were doing indefinite integrals, let me kind of get you to one like this, we didn't get a numerical answer because we didn't have the bounds. So when we didn't have the bounds, our answer was in terms of a function, not a number. Oops, went too far. So what is that number representing? So if I have this curve from A to B, that number is that exact area. So, all right. So you no matter, it doesn't have to be lines, it doesn't have to be circles, it can be any single function going on, okay? And we can find this area. Is your mind blown? Because it should be. All right, so let's look at this one. Okay, so I want to evaluate the definite integral. So now we know it's a definite integral because we've got these numerical bounds here. So the first thing I'm going to do is I'm going to take the antiderivative and I'm not going to use a plus c because it would just cancel away. And then I'm going to say, this is like this right here is saying I'm going to evaluate that function from -1 to 2. So then I plug in my 2. And that's my f of b part. And then I plug in my -1. That's my f of a part. So I am doing my f of b minus f of a, and then I go simplify to get my value. So if I was to look at the graph of this, let's just look at it really quick. So let's go to our y equals and type in x cubed minus 4x squared plus 1. And we're only really looking at it from -1 to 2. Let's just sketch that really quick. So -1, we'll just kind of get what this is looking like, okay? And I'm only looking from like -1, maybe like right here, all the way until 2, which maybe looks like about right here. So this area that I have accumulated is more negative than positive. Hence why I got a negative area, meaning more was below than above. And to get that area, it took the area above and subtracted the area below. And that totaled to negative 21/4. Are you guys excited? Okay. So let's look at this next one. So it's a little bit trickier. So let's do the graph of this right here. Okay. So I'm going to go ahead and factor. Let's get the graph. Let's see what that looks like. So I'm going to take an x out, and I have negative 3x plus 8. So I know I have my zeros at 0 and at 8/3. So my graph has a 0 at 0 and 8/3. And this was a parabola that was frowning because it's got a negative for the leading coefficient. So it looked something like that. And then, lo and behold, we went and took the absolute value of it, meaning everything below had to become above. So now my graph looks like this. So if I was going to go from negative 3 to 3, then I'm going to have to separate into 3 different pieces because I do not know integrate absolute values. I need to go make it kind of a piecewise. And I can spell piece. Okay. Okay, so we are going to integrate first from negative 3 to this guy of 0. And that one we had to flip. So we're going to integrate the opposite signs. Then we're going to add on the integration from 0 to 8/3, but we did not have to flip this part, so it gets to stay exactly as it was. And then we're going to add on the integral from 8/3 to 3, and we had to flip, so we have the opposite signs. Oops. And then I would do the fundamental theorem of calculus on all 3 of those pieces. Now, if this was a calculator problem, then awesome, because in my calculator, I can put in the absolute value bars. So I could go math 9, and I want to look from negative 3 to 3, and I'm going to go take the absolute value of what we had, negative 3x squared plus 8 dx, and it will give me the answer without having to break it all into pieces. And I'll tell you what it gives me. It gives me a decimal approximation of 40.8372. Okay. Now, I could get an even better exact answer. The calculator wasn't able to do that for me, but I could do that if I did all of 3 of these by hand. So what is that absolute value? Why would we ever be using the absolute value inside of an integral? What the heck? Well, we've discussed this before, that if I look at the velocity graph, maybe from like here to here, if this is velocity, when I take the absolute value of velocity, okay, then I get my speed. And when I do this, I can get this area under here, the area under here, this area. When I flip it all up, the area under the velocity graph is the total distance. If I left it as just velocity, then I'm going to have the negatives and the positives that are canceling some, and I have that displacement. So if I want the total distance, we have to have the absolute values of the velocity. Now, I've seen kiddos who try to do this. That is not correct, okay? That means that you just take your answer and make it positive. So whatever this answer ended up being, all I did was take the absolute value of that answer. So that is wrong. Make sure that you are putting the absolute value bars on the inside. Okay? All right. Let's do some vocabulary. Then we'll get to some more concepts or we are going to do some exact problems. Okay. So to find the new position of a particle on the x-axis, add the starting position to the integral of the velocity from starting time to the new time. Okay, so the new position, that's kind of like where am I going to land at? That's my displacement. So I don't need absolute values or anything like that. It's just where am I now? Okay, so to find the total distance, here we're going to integrate the absolute value of velocity, which is the speed. Okay, so here, let me cross out what we've used. Oh, here, it's right there, which is the absolute value of the velocity. And 3, to find the change in the position, we're going to integrate the velocity. That is the displacement. Okay. Okay, let's try this next one. So here's a graph. And it says that this is the velocity graph. And then it gives me an original position. So at t equals 2, I know that I started at 5. So as I kind of look at this with the velocity, let's see what this area is. 1/2 base times height. Base was 1, 2, 3. Height was 2. So this area is 3. Let's see what this area is. 1/2 base times height. This would be -2. So I started at position 2, or position 5, and then at this place, so this was at time 2, at time 5, I would have added on 3 to be at 8. And then at time 7, I would have subtracted 2, and then I would have been at 6. So that's kind of like helping me to see that distance, okay, the displacement. If I wanted to get the total distance, then I'm going to take the 5 plus the 3 plus the 2. Does that kind of make sense? Okay, now if I just want to know how much of the total distance it's accumulated, then I wouldn't worry about the 5. All right, so go see if you can match A, B, and C to that 1, 2, and 3. And then let's see if you did it right. You can pause me. When you're ready, unpause. All right, if you struggled with that, let me know in class. All right, same thing here. I want you to see if you can match these guys. Go ahead and pause me, and when you're ready, unpause. And see how you did. Okay, so the next thing that I want to do is this part 4. I want you to try it and to pause me. It's a little bit different now. Instead of giving me a function, it's giving me a table of values. And so I want you to try this. It's getting a left remote on. Pause me. When you're ready, unpause. All right, very good. And then this is just for you. You do this for you. Make sure you know what all of these are, okay? And I know I've put what helps me and what I am putting on my paper may be a little bit different than yours. Okay. And then I know that we have 3 different AP problems, but I want to do all 3 of these together in class. Okay? Because I really want to make sure that when we get to these tougher ones, that you can ask me those questions because they're very conceptual. All right. So, got some of the basics. We're going to see more of the advanced here in a little bit in class, and I will see you soon.